right, before we start our next section today, I want to go over one of the homework problems that you may have worked on yesterday, depending if you got to it or not. So can we open up to page 38? We're going to take a look at the piecewise function, number 10 at the bottom. We did a lot of these yesterday and the day before. We were practicing kind of some strategies to help us go through these. And if you had a chance to do it, hopefully this is what you got. If you didn't do it yet, make a mental note, okay? But I want to go over the domain and the range. So let me make these a little bit more obvious first off. You still can't see that. There we go. So if you were to graph this piecewise function, this is what we would have. The domain and range we want to analyze. When you hear those words, what do you think of? Domain, range. What are we looking for on that graph? Yeah?
The limits.
What do you mean by limits?
Like how far it can go before it stops.
Okay, so we're looking for the limit of what variable for domain? X. Good. Okay, so we're looking for the lowest x value, highest x value, those, if you want to use the word limits, that'd be great. Okay, so, and then for the y's for range. We did a few of these, I think, previously, but the graph we analyzed was not as complicated or involved as this one is. So we're going to go over how to do this one. Again, we're going to have many more practice examples throughout this section, but I want to do this one together because it's a little bit different. So we want to kind of think about which x values are we allowed to plug in to this graph or this equation. And since the x-axis goes left and right, I want us to drag our pencil left and right, okay, as that visual aid. So when you put your pencil on the left-hand side, you kind of need to ask yourself, how far left does the graph go, or where does the graph start? Can we figure out that x location? How far left does it go, or where does it start? Good, Matt?
-9.
-9. Okay, so that's this spot right there. As we continue to drag our pencil across, you need to ask yourself, where do I come to a spot that does not have an x value? Meaning there's no point at that x value. Can we find one? Let's see, as we drag across from -9, the graph looks pretty good until we get to -1. Do we have a point somewhere at -1? Yeah, we have that closed circle right there. Even though this one's open, we still have a point at -1. So we can continue to drag our pencil. What happens at 3, though? Do we have a point at 3? No, because we just have that open circle, right? So this is where the graph begins at -9, but we encounter an x location that does not have a point or a graph there. So we're going to say that that ends at 3. Now I know we still have more graph to go, but you're creating an interval, like a beginning point and an ending point, that includes all the values in between them. So we got to ask ourselves, can we include -9? If you were to plug in -9, would you get a point out? No, because that's an open circle. So that's when we use a parenthesis to denote that idea, that you cannot plug in that value. And we would also need a parenthesis on 3 because we had another open circle there. So you can plug in anything you want between -9 and 3 and you would get a point out on your graph. Now since we have more graph to trace, we're going to use a capital U after that interval. That U stands for union. Like if you get married, you're in a civil union. It's like bringing two people together. So what we're going to do is bring these multiple intervals together. Okay, we have something else to write over here. So we previously stopped dragging our pencil at 3. That's where we will pick up our next interval. And as we continue to drag your pencil, you got to ask yourself, when does the graph stop? Or how far right will that graph go? What do you think? Where will it end? Is there something on the graph that kind of hints us to this idea? What do you think, Matt?
The arrow.
The arrow. So that means what?
That it never stops.
Never stops. Okay, so we can go on for infinity if it's never going to stop. So here's another interval. We got to ask ourselves, do we need a parenthesis or a bracket on those values? We had an open circle at 3, so we cannot include that. And you will never ever reach infinity, so we cannot include that either. So this is our domain for this graph. You're telling me little intervals of x values that you could substitute in. Okay, a little bit more involved than the last one we did. So drag your pencil across, and you got to ask yourself a few questions. Where does the graph begin? How far left does it go? Do I ever come to a spot that does not have an x value? Okay, because we'd have to skip over that. Notice how we skipped over 3. And as you continue to drag your pencil, ask yourself, when does it end, or does it ever end? Maybe you need that infinity. Okay, so we're going to do the same concept, but instead of dragging left to right, now we're going to go low to high, okay, for the range. So we're going to ask ourselves the same question. How far low does the graph go? Or where does the graph begin at the bottom? Can we figure out that first interval value? How far low will it go? What do you think, Noah? Why? Okay, so this arrow kind of means two things. Not only does the arrow mean it's going to continue to the right, but the arrow also means it's going to continue down. Okay, so two things. So it'll begin at negative infinity. As we continue to trace up our graph, we got to ask ourselves, do we come to a y value that we cannot include? Is there an open circle somewhere? Okay, this open circle. And what's the y value there? Yeah, -4. Okay, so here's our first interval. We can begin at negative infinity, and we have to stop at -4 because there's no graph there. Okay, there's an open circle. Will you ever reach negative infinity? No. Can we include -4? No, because there's an open circle. Clearly, we have more graph to trace. So we're going to throw in a u because we have another interval to write. Now since we left off at -4, okay, and the graph continues after that, that's where our next interval will begin. Okay, so right now we're at the x location of -4. As we continue to drag up, when do we hit another roadblock, if you will? Is there another y value that does not have a point? What do you think, Lainey? 0. Okay, that would be this value here. Is there another open circle before 0, though? -2. Okay. So we started at -4. We cannot touch that because it was an open circle. And we have to end at -2 because that's another open circle. So that'll be a parenthesis. We clearly have more graph to trace. So we need another u. We're going to have another interval. So right now our pencil's at -2. As we continue to drag, we got to ask ourselves, where does the graph begin again? Lainey, this was the one that you said previously. Okay, it's going to start at 0. All right, the y value of this open circle. And as we continue to drag, when will the graph stop? Looks like 1, 2, 3, 4, 5. Can we touch 0? Bless you. No, because we had an open circle. Can we touch 5? Yes, there's a closed circle, so that's where we need a bracket. Okay, so we're going to drag our pencil left to right for domain and then low to high for the range. This one was extremely involved. Okay, but we're going to see more of them throughout the unit. Okay, it'll start to sink in eventually. It's all about the dragging though, and you'll learn to look for holes. We'll eventually talk about asymptotes. Okay, but for right now, not too bad. Okay, so that was part of your homework. Let's take a look at page 39 though. We're going to go ahead and start our next section. This is going to be somewhat of a review. Okay, a little bit because we did some of it earlier at the beginning of the year. We're going to take a look at function notation again, but we're going to start to make a connection between the math that we calculate and what that means or represents in terms of a graph or a picture. Okay, so we're going to make this connection between the two. Hopefully at this stage in your mathematical career, we know that, if you could see it, the y variable means the same thing as f of x. Okay, f of x and y mean the same thing. What we're going to do is take a look at this quadratic function. It's a power of 2, and we're going to analyze some of these function values. Now, it's not asking us to identify any transformations, but just for practice, can we take a look at that equation and pick apart some changes? I'm hoping we're getting kind of quick with these. Take a look at how that is written, and what do you notice? Go ahead, Olivia. It's a parabola, okay, quadratic of, or power of 2, so we have that U shape. That's the parent function. So we would start with that, and then what are some changes? You want to keep going? Yeah. Up 4, good. Any other ones? Yeah?
Got a vertical stretch by 2.
Vertical stretch by 2. Okay, so we're making it taller. We're changing that slope. Okay, instead of a slope of 1, it's now a slope of 2. So we're making it taller. Up 4, vertical stretch by 2. You want to keep going? Yeah?
X-axis flip.
X-axis flip. One more. Kind of the tricky one. What's the plus 3? Good, Lainey? It is left 3. Okay, so this is a function. Let's take a look to see if the graph makes sense. Okay, so this is actually the graph of that parabola. It is a U shape, so that's checking out. If we were to move the vertex, it would be left 3, up 4. Notice how that checks out. It is upside down, so we had that x-axis flip. And the vertical stretch is a little difficult to find. If you did a slope of 2, okay, you would find another point on your graph. That one's a little difficult. So it looks like this graph is checking out, okay, based off those transformations. What if I wanted you to find f of negative 4? What's that asking us to do? Or what does the negative 4 represent? What do you think, Lainey? That's an x value. All right, so I want you to plug in negative 4 into that x and see what you get. Negative 4 plus 3 is negative 1. Square it. We get positive 1. Times negative 2. Add 4. We'll get 2. What does that answer of 2 represent? Go, Blair? The y value. Good. Okay. So we're plugging in a number, getting out a number. Input, output, x, y. Try the next 2. Negative 4 and negative 14. Check out. All right, so here's the connection. We can do the computation, okay? We can do the math, but we got to ask ourselves, what does it mean? So take a look at this one. When you found the value of f of negative 4, we said that was 2. Okay, f of negative 4 equals 2. What does that mathematical notation tell us about the graph of the function? What do you think, Blair?
It's going to be a point there.
It's a point. What is the point?
Minus 4, 2.
There we go. We said this was an x value, this was a y value. If you know an x and a y, you know an ordered pair. So the point negative 4 comma 2 is on the graph. And if we actually check it out, let's see if it's there. Negative 4 comma 2, boom, there it is. Okay, so if that's what the first calculation tells us about the graph, then the other two that you did probably mean the same thing. So f of negative 1 equals negative 4. That means we have the point negative 1 comma 4, and f of 0 equals negative 14. We have the point 0 comma negative 14. Are those on the graph? Did we do our work correctly? Because we have this connection, this relationship. Let's see, negative 1 comma negative 4 looks to be good. Now 0 comma negative 14, we don't have that on the graph, but it kind of looks like it would be there, right? If it were to continue down. Okay, so I say we did that pretty good. So whenever you're plugging in these numbers and getting numbers out, you're really used to doing that in your math classes. You're actually finding points, okay, ordered pairs that relate to a graph. Now, if we think about or start to analyze a graph a little bit more, we can take a look at what are called zeros on a graph. We briefly mentioned this word earlier, but what's a synonym for the word zero? What does it mean graphically? What do you think, Matt?
Intercept.
Which one?
Either.
Either, maybe. It is an intercept. The question is it the y-intercept or the x-intercept? It's one in particular. What do you think, Elsie? The x-intercept. Okay, so it's called the x, or it's called a zero because the y value of the x-axis is 0. Another synonym that you might have heard or seen before is the word root. If you think about roots of a tree, the roots normally start at ground level, and graphically we kind of consider the x-axis the ground, so roots happen at that location. So there's another synonym you might be able to use. So if we take a look at the graph, clearly we have an x-intercept somewhere between, let's say, negative 4 and negative 1. Okay, we have it crossing or touching the x-axis there. But it's nice that we have that picture. I want to know if we did not have the graph, okay, kind of tune it out for a second. How can we confirm, based off the calculations that we did, that we have an x-intercept somewhere between negative 4 and negative 1? How can you tell based off the numbers? Kind of hidden math. Can we find it? What do you think?
It goes from a positive to a negative.
There we go. Notice how this 2 was a y value, which means this negative 4 was also a y value. If the x-intercept, or x-axis, has a y value of 0, isn't 0 between those two? So if you go from a positive number to a negative number, you must have been 0 at some point, right? Okay? If you take a look at the other ones, negative 4 to negative 14, we do not have that sign change. There might be an x-intercept in here. Okay, there could be, but we don't know for sure because we don't see that sign change. So we can confirm based off of computations if we have an x-intercept, not just solely relying on the graph to actually find it. Okay, so let's go ahead and say that f of negative 4 equaled 2 and f of negative 1 equaled negative 4, and the y value of 0 is between 2 and negative 4. So we must, okay, it is guaranteed, we must have an x-intercept between the x value of negative 4 and the x value of negative 1. Okay, we had that sign change. We went from a positive y value to a negative, so we have to cross 0 at some spot. We don't even need a graph to figure that out. Okay. But what is nice is since we have a graph, maybe we can become a little bit more specific on where this x-intercept is located. So right now, we're saying that the one x-intercept is between negative 4 and negative 1. That's not a bad interval. Okay, it's only 3 units wide, but we could probably make that interval a little bit smaller. So based off of looking at the graph, what is maybe a smaller interval that the x-intercept might be found in? Instead of saying from negative 4 to negative 1, can we get even closer? Between what two x values is an x-intercept found based off the picture? Do you see one, Blair? Yeah. All right, so this x-intercept, we can get a little smaller interval between negative 2 and negative 1. Notice how that interval is only 1 unit long instead of the 3 that we had previously. So even though our computations gave us an interval of 3 units, actually looking at the graph might help us narrow it down to 1. Okay, we can get a little bit more accurate. Now there is another x-intercept right here, and it looks like that could be between negative 4 and negative 5. Okay, so we can kind of confirm x-intercept 2 ways. We can look at computations. Do we have that sign change, like positive answer, negative answer? Or we can simply take a look at the graph and try to figure out between what 2 values it might be. Okay, so these are guesses. Notice how we're having intervals. We're not actually finding exact x-intercepts, but we can do that in a second. Okay, we ready to flip? Am I going too fast? Okay, let's flip it. So on the back, we're going to take a look at the same function, all right, and it's the same graph, but now we're going to take a look at different notations or questions it's going to ask us. What does f of x equals 0 mean? What's that asking us to do? Or what might the 0 represent? All these different questions you can ask yourself. Yeah?
Find the value of x when y equals 0.
All right, so remember, f of x and y are the same thing. So this is basically telling you the y value is 0. Let's go ahead and try to figure that out. So we'll set the equation equal to 0, and we're going to solve for x. The question is, where do you want to go from there? How can we get that x all by itself? You have an idea, Lainey? Subtract 4. Okay, if we want to get an x all by itself, we want to start moving things to the other side of the equation. Okay, isolate that x variable. So we'll go ahead and subtract the 4. Can we keep moving things over? What do you want to do next? Good. No, not Rachel. Not Rebecca. Julia. Divide negative 2. Good. All right. Next, we're going to keep moving. What do you think? Good, Nick? Square root. Good. Okay, so square root both sides. Get rid of the power of 2. Now, whenever you square root both sides of an equation, I'm hoping we've seen this symbol before. Have we seen plus or minus? Yeah? That's only when you square root both sides. We need to put that in there. So we'll have the square root plus or minus the square root of 2. Lastly, we can subtract the 3 over. So we have exact answers right here. Okay, notice how there's no decimals, no fractions, exact answers. If you want to get a decimal answer, we can type that into our calculator. And we should actually get two answers because we can use either the positive square root value or the negative. So if you happen to type those in, I think the positive version, we'd get negative 1.586. I know you don't have calculators in front of you, but if you did, this is what you'd get. And then if you were to type in negative square root of 2 minus 3, we'd get negative 5, or negative 4.414. All right, so those are our x solutions, and we happen to have two of them. Okay. Do you think you guys can do the next one? You definitely don't need a calculator for this one. Can you give it a shot? All right, so we can subtract the 4, divide the negative 2, square root both sides, don't forget the plus or minus, and then subtract the 3. What were our two answers then? If we do the plus 2 and the minus 2 separately, what'd you get? Good, Blair? There you go. All right, so positive 2 minus 3 is negative 1. Negative 2 minus 3, we get negative 5. All right, two solutions. So these are wonderful. These are computations. These are answers. These are results. But we got to think about what does this mean in terms of the graph. Okay, what are we finding? So if we think about these first two answers, when we did f of x equals 0, what do you think these decimal values represented on our graph? Can we find them? What do they mean? What did we say this 0 represented? This was a y value, right? Okay, so a y value of 0 happens to be the x-axis. So if you have a y value of 0 and these are your x spots, it looks like we just found x-intercepts. Okay, so whenever your y value is 0, you're finding the values of x-intercepts. So on the previous page, we found the interval where the x-intercepts might be located, but now we actually did the calculation. Okay, we know where they are exactly. So we got a little bit more specific. What if we did the other one? Okay, f of x equals negative 4. Our answers were negative 1 and negative 5. Where are those on the graph? Can you describe them? What do you think, Noah? There you go. This is a y value, right? So if you take a look at the y value of negative 4, notice how your graph should have 2 spots or 2 points, and that's what we got here. the x location of the first point was -1, the x location of the second point was -5. So the points, let's see, -1, -4, and -5, -4 are on the graph. Okay, so we're starting to get used to this connection. You're used to plugging in numbers, getting out numbers, their answers, they're great, but what do they mean? Okay, how can we make that relationship between mathematical work and the graph of a function? Okay, we're going to get really used to analyzing equations, but also graphs this year, and how they're related to each other. So I know sometimes the notation can get confusing, okay, when we're using all these different symbols and things. So just as a summary, if we have the notation f of a, where a is a number, what is that asking us to do? Or what are we trying to find? However you want to think about it. What does that a represent? For instance, if I did like f of 3, put a number in there if it helps. What is that notation asking us to do? Yeah?
Find the value for y when x equals 3.
Alright, so this a number, whatever it is representing an x value. So we can say x equals a, we want to find the y value. So plug it in for x. Okay. On the flip side, we have a very similar notation with f's and a's and x's and things, but it looks different, so it must mean something different. This time we have f of x equals a. So what does this a number, plug it in for a number if you want to, what does that a represent, and what are we trying to find? What do you think, Carter? There we go. This time we have a y value, and we want to find x. Okay? So depending on the way it looks, you're finding an x value or a y value, and therefore you know an ordered pair, okay, on the graph, x comma y. How are we doing so far? Okay, we're going to relate this function notation to some of the graphs and equations that we've been talking about, like square roots, absolute values, cube roots, cubics. Okay, so this is, we're going to kind of amp it up a bit. Let's go ahead and take a look at the next page. We're given a graph, but not an equation this time. Okay, so we only have one piece of information. Notice how it's a V-shaped graph, so we would probably have an absolute value equation. And I lied, they actually did give us the equation. It's at the bottom. Okay. Does the equation make sense? Take a look at the V shape. The vertex is at -2, 5. So that means if it started at the origin, it went left 2 and down 5. We can identify those based off the equation. Okay, so the graph and the equation make sense. Let's go ahead and take a look at some of these function values. So g of -6. Let's go ahead and find it. Now if we look at the graph first, this is representing an x value, so we'll go to that spot, and we want to find a y value. Looks like that would be a y value of -1. But let's go ahead and confirm it based off the equation. Okay, can we actually do the computation? So based off the equation, if we plug in -6, let's hope that we get an answer of -1. So -6 plus 2 is -4. Absolute value of -4 changes to positive. 4 minus 5, -1. Okay, so it checks out. We can confirm from the equation that the graph looks good. Check out the next one, g of 1. If we were to plug in 1 into the graph for an x value, we would get out -2. Let's go ahead and confirm that based on the equation. So we'll plug in 1 for x. 1 plus 2 is 3. Absolute value is still 3. 3 minus 5, negative 2. Okay, so we're confirming the results based off the graph. What about the next one? G of x equals negative 4. What should we be anticipating for that notation? What does the negative 4 represent again? A y value. Okay, so this time we have a y value of negative 4. And if we take a look at the graph, we should have two solutions. Okay, so it looks like our x solutions should be negative 1 and negative 3. Okay, that's based off the graph. But half the battle is trying to confirm it based off the equation. So let's see if we can do that. So we're going to set the equation equal to negative 4. Okay, that was our y value. We have 1x. How do you want to go about solving for x? Can we start moving things to the other side? Maybe add 5. We get 1. Where do you want to go from there? We're supposed to get two answers. What do you think, Travis? There we go. Good. Do we remember doing this way back in Algebra 1? Yeah? All right. So an absolute value can mean two things, right? I don't know what's going on. If you plug in a number, okay, a positive number, the absolute value isn't going to change anything. But if you plug in a negative number, it's going to change it to be positive. So we're going to have kind of two outcomes here, whether we plug something in that's positive or whether we plug something in that's negative. So that's why we keep a positive one or we switch it to a negative one. So if we solve, subtract the 2, we get negative 1. And if we subtract the 2 on this one, we'll get negative 3. Notice how we can computationally, okay, algebraically confirm what the graph is telling us. All right, let's go ahead and try another one. So this time we have a y value of 5. We unfortunately do not have a graph that goes up that high, so we can't anticipate what the answer should be. We really only have the choice to use the equation. So the graph is wonderful as long as you have the information provided to you. Okay, maybe the window is not good enough to help you with some of these questions, but all hope is not lost. We can use the equation. So let's go ahead and get the x all by itself. We can add the 5 over. We should probably be anticipating two answers like we had on the previous one. So let's go ahead and break it up. We'll have a positive 10 or a negative 10. And looks like we get 8 or negative 12. We doing okay so far? All right, we'll stop there for today. Tomorrow we're going to do a similar problem. This time we'll take a look at a square root, and maybe we'll get into some other of those parent functions that we discussed in the last section.